let's do it. So I'm working through chapter summaries for the first half of Introduction to Electrodynamics, 4th edition Griffiths, and we are in chapter 5, Magnetostatics. And you may be saying, hey, I can already see the board. That's not magnetostatics. Yeah, I know. It's what we've done so far, and it is kind of related to what we're going to do. And I know we're going to get to it in a little bit, but I want to just talk about some of the things that we've done because these are the important things we have so far. So we have this as the electric field due to a charge distribution rho, charge density. We also know that these two equations are describing the electric field, the shape of the electric field due to point charges, right? So this says that the divergence depends on the charge density, but there is no curl to the electric field in magnetostatics. Okay, that will change later. With this, we can define an electric field as the gradient of a scalar field, and we call that scalar field the electric potential. And then from other things, we can create the electric potential as the integral over charge density rho. We did that already, okay? So I don't want to go into all the details. And then finally we get to this. We said that if we use this for the electric field and we combine it with Gauss's law right there, we get the Laplacian of the potential is negative the charge density over epsilon naught. Okay, we're coming back to that, but I was wondering, we already did that. So we don't need that again. Now let's go ahead and start on the key things here. This book starts off with the Lorentz force. This says that if you have a charge in an electric and magnetic field, then we have QV cross B for the force on the particle due to a moving charge in a magnetic field. And then you also have the electric field. So QE is the electric force. So both of those together. Now, the cool thing here is that this is going to be perpendicular to the velocity, and this is going to be in the same direction as the electric field. So you can set up situations where the magnetic force and the electric force are in opposite directions to each other, and you can create some pretty cool things. I'm not going to go into all the details. I do want to point out one thing, just because it's really cool. For circular motion, if you have an object in a constant magnetic field, it's going to move in a circle, right? Because the velocity, the force is going to be perpendicular to the velocity because of the definition of the cross product. And when you have a force perpendicular to the velocity, it turns, it changes direction, and it'll keep moving in a circle. So if it's moving in a circle like this, here's your velocity, the magnetic force is that way, then you can say QVB. I'm going to say it's completely perpendicular, so we don't have to worry about I'm just talking about the direction. And that's going to be mv squared over r. That's the mass times acceleration, right? That's Newton's second law, and that's the centripetal acceleration, v squared over r. So you could solve this for the radius of orbit, and one of those velocities cancels, and you get mv over qb. But the cool thing is, and this is just one of the examples, it turns out that as you increase the velocity, you increase the radius of a circular orbit, but you don't change the period of how long it takes to orbit. The period is constant. So this is a cyclotron. So the idea of a cyclotron is that you put you have these two metal Ds with the magnetic field going through them, and these change electric potential. So that creates an electric field. In fact, it'd be this way. So when a charged particle comes right here, it accelerates. And then while it's back in this D, you switch the potential, and then when it comes over here, it accelerates that way again. So it just accelerates again and again, and goes in a bigger and bigger circle. But this frequency right here is set. You don't have to adjust that as these things go around. And that's what makes it really easy to build. And you can get particles up to high speeds. But that's just an example. I like it. Okay, what do we have next? Oh, now, what if I don't have a charge, but I have a wire? And it looks something like that with a current going through it. Well, I, or QV, is just like IDL. So I can find, if I take a little piece of this and I'll call it a vector DL, then that little piece can experience a force in a magnetic field, so that the force would be DF is IDL cross B. Now, if I want to find the total force, I'm going to have to integrate along that weird path, whatever it may be. So this is going to be the integral of I dl cross B is the force on a wire. Right? Each little piece is like QV. Next, we have two really cool things. One is surface current density, K. This is the basically the surface charge density times the velocity. And then we have the current density, which is the charge volume density times the velocity. And these also are just like QV. But just like here we have I dl is like QV, using the surface current, this is going to be equal to K dot n hat dA, and where n hat's the direction of the thing, and we have J dV is also, no, it's just K dA, J dV. So these are all equivalent terms, right? So if I know the volume density, the current density J, I can replace I dl with J dV. That comes up a lot, so I just want to point that out right there. Based on the definition of current, the flow of charge, we also get this. The divergence of the current density is negative. Yeah, negative the rate of change of the current, the charge density. Right? That's the same thing as the definition of current. Okay, now we get to finding magnetic fields. So the first way we can find a magnetic field is Biot and Savart law. Let's start off with a charged particle. And there is one little bit weird thing here. So suppose I have a charge Q with a velocity V. It's going to make a magnetic field. And I'm going to draw that for you in just a second. But we can calculate that magnetic field as B mu naught over 4 pi QV cross R hat over R squared. So in this expression, R is the vector from the moving charge to where we want to find that, that electric magnetic field. So imagine that I actually have 3 vectors. We did the same thing for electric fields. So suppose I have this RQ, the location of the charge. I have this RO, the location I want to find the magnetic field, and then I have this R. So that's that R. R is equal to RO minus RQ. That's really important if you want to find the magnetic field due to a moving charge. It's going to be important if you want to find the magnetic field due to a current distribution. Right? We have to find that vector R. Now, again, the book calls these things different. I can't remember. I think it calls that R, and no, the script R. I forget, and I don't want to say it because I'll mess it up. But I like to use that notation right there, and that's a V. So if we do that, because we have the cross product, and also some places we'll put this as mu naught over 4 pi QV cross R over R cubed, because remember R hat is R over the magnitude of R, so those two things are the same. But because we have this cross product, it's going to give us a magnetic field that's perpendicular to the velocity and perpendicular to R hat. So suppose I have a charge, a positive charge coming out of the board. Then this is going to make what I like to call a curly magnetic field. And it gets smaller as you get further away. And it's easier to draw in 3 dimensions, but I can't do it on the board. Okay, so that's a picture that you want to think in your mind, the magnetic field due to these wires. Of course, we have the right-hand rule for cross products, but we also have the right-hand rule for the magnetic field. If you put your thumb in the direction of QV, not V, QV, then your fingers of your right hand curl in the direction of the magnetic field. So I like to treat QV as one single thing. Okay, that's Biot and Savart. Now, what if I have not a charge, but instead I have a current? Well, remember, we had this relationship. I can say B is mu naught over 4 pi, the integral of I dl cross r hat over r squared. Because I can replace QV with I dl, and I get the magnetic field just due to a little piece of the wire. If I wanted to do the whole wire, then I need to integrate. And remember, you're going to have to find that r because different parts of the wire, if I want to find the magnetic field right here, these different parts all have different r's. Okay, so you're going to have to set up an integral. And I have a video on that. You know I have a video on that. But this is just a summary. This is not everything. A summary. Okay. Well, we can also write this as, remember, I can replace I dl with mu naught over 4 pi k dA cross r hat over r squared, or I could replace it with mu naught over 4 pi j dV cross r hat over r squared. And a lot of times we'll move that dA over there and move that dV over there. It's a scalar value. Okay, those are all equivalent. Okay, where are we? Okay, now we're ready for another way to find the magnetic field, and that's Ampere's law. So let me write real quick up here. We had this del cross E is 0. Del dot E is rho over epsilon naught. Gauss's law, and this we just called, it's not even true because it is not 0 if you have changing electric fields and changing magnetic fields. But now if we do the same thing, this says that electric fields due to charges are not curly at all, but they're divergent. Well, we have something similar in that this, well, I'll write it out. I'll write it out the long way, the integral way. We have this is Ampere's law. This says if you take the magnetic field and integrate around a closed path, that's going to be equal to the current passing through an area that crosses through that path, okay, any area. And just like with Gauss's law, this allows us to find expressions for the magnetic field if we make assumptions about the shape of the field. So it doesn't really give us it all the way. The differential form of this, if we can use Stokes' theorem and get this, del cross B is mu naught times J, the current density. But you'll notice up here, this says the electric field isn't curly, the magnetic field is. But if we do the same thing up here, the divergence of the magnetic field is 0. Okay, so they're like completely opposite fields. Divergent, not curly; curly, not divergent. Okay. Now, because finally we have 2 more things. One is the vector potential. And let me just put it back up here again really quick. We said that the Laplacian of the potential is negative rho over epsilon naught, and that led to 1 over 4 pi epsilon naught rho dV over r. We had that. That was for electric potential. Now, we have the following. It's possible we have this, del cross B equals mu naught J. That's the Ampere's law. Because it's possible to say del cross A is equal to B. And if I put that in as del dot del cross A equals 0, that's true, right? I can do that. That's okay. Now, if I put this in up here, I get del cross A. We call A the vector potential, the magnetic vector potential, because it's a lot like the electric potential, but it's a vector. Potential. Why can't I spell that? Okay. This is by definition equal to, what did I write? I wrote it down wrong. It's by definition equal to del of del dot A minus del squared of A. That's just a vector identity. If we choose, this is important, choose del dot A to be 0, we can pick that. Just like we pick v is equal to 0 at infinity. We pick that. Okay? If we pick this, we don't have to, but if we do pick that, then we get this is del cross B, which we know is mu naught J. So we get del squared A is negative mu naught J. And that is very important. But it's a choice. It's not always true, like I said. But look at this. It looks like that, except this is a vector Laplacian, the vector, and that's a vector, and this is scalar. But we can break this into 3 equations in Cartesian coordinates that say the Laplacian of AX is negative mu naught JX, the Laplacian of AY is negative mu naught JY, X, the Laplacian of AZ is equal to negative mu naught JZ. Now, mathematically, this is identical to that, which means that AX should be identical to this, and AY should be identical to that, and AZ should be identical to that. So we get the following. A is mu naught over 4 pi, right? Because here we had epsilon on the bottom, here we have mu naught on the top. That's why that's up here. And then we're going to integrate J dV over R. And this is the vector potential. But look right here. Look right here. So this was in class. We were talking about this in class. And one of my students goes, hey, look, that's what's on the front of the book. I never paid attention. I'm like, oh, yeah, finally. So it is kind of a big deal to write those. Now, you may think, well, why do we even care? Why do we care about electric potential? It allows us to solve problems that we couldn't otherwise solve. And in particular, in this case, the magnetic vector potential also allows us to solve problems that can't otherwise solve, and we'll use it again later. It'll become very important later. But right now, this allows us to derive the magnetic dipole moment, just like we derive the magnetic dipole moment due to the electric potential. So let's think about the magnetic dipole moment. I'm not going to derive it, but the magnetic dipole moment is very important. Okay, so the magnetic dipole moment, the easiest one is to say, okay, suppose I have an electric current I going in a loop, and so this has an area A, that's I. Then we can define the magnetic dipole moment here as I, A vector, where A vector is in the direction perpendicular to the area. Of course, there's a more generic version of this. M is equal to 1/2 the integral of, well, I already forgot it. Yeah, it's R cross J dV. So if I have some current distribution, current density J, I can find the magnetic dipole moment by integrating too. So you can do it for anything. And just like before with the electric dipole, it's an expansion, right? We can take any charge distribution and expand it as a monopole term, a dipole term, a quadrupole term. But if I have a current, I can just expand that as a dipole term. Now, the vector potential due to a dipole is mu naught over 4 pi. And I forget all these things because there's a lot of stuff here. M cross R hat, that's right. M cross R hat over R squared. Now, if I know the magnetic dipole, the magnetic vector potential, I can find B. It's the curl of A. So with that, I get the magnetic field due to a dipole, mu naught over 4 pi. I do remember this one. 3 m dot r hat minus m over r cubed. How to remember that one? Because it's the same form as the electric dipole moment, except we're dealing with magnetic dipole moments instead of electric dipole moments. That's what's so great. The mathematics and the shape of these fields are the same. Okay, so that's that. And we will definitely use the magnetic dipole moment in the next chapter. The end. Hope you enjoyed that.